probably try to do a little bit of, we'll see if we can get people out here maybe with a little food or snack or something, and so we can kind of meet each other a little bit more. But for now, it's great to have everyone in virtual and those that can be here as well. So Robin Morris is going to talk today about something that we all probably have to do more of, which is reading, and how that relates to our brains. So take it away, Robin.
All right.
And this is, by the way, one of the focus sub-projects that is part of the dynamic sub-project. So focused application is part of the dynamic sub-project. So we're going to be collecting some data in readers and
I didn't share.
Doing concurrent EEG, fMRI, and brain stimulation, and then use that data set as an exemplar data set for evaluating different methods to study brain activity and its links to reading. So.
You got it.
Hey.
All righty.
All right.
There it is. I'm not an imager. I study reading and atypical reading development, especially kids who can't learn to read and adults who never learn to read, and are interested in those individual differences in why that happens. And clearly, one of our theories is that there has to be something in the brain that's making this difference. And the main thing that's sort of interesting is that this is not a general problem in children and adults who can't learn to read. They have good cognition and other nodes and areas of the brain and functioning. It's a very localized thing. And the question is what's going on locally that's really restricting them from learning to read. We have a statement in our field that basically everyone's born dyslexic. It's just some of us are cured along the way, okay? Because none of us really are born learning to read and know how to read without education. So let me give you a quick overview of sort of what we think about reading and why we think it's connected to some of the systems in the brain and what we've been looking at, so you have an idea of some of the things we're interested in doing in the CREST grant. Just real quickly, reading is really visual language. It's basically a map of the language system that reading sort of takes as this foundation. For those of you who know anything about, does this have a pointer on it? Or do I need to do that on here? Okay.
Yeah.
That's good. So some of y'all may know about Wernicke's area, which is in the superior temporal lobe, and you have the Heschel's gyrus, which is the auditory system, and of course that's all connected to the Broca system and IFG and all the kind of fun stuff here. So the language system we're sort of born with. Evolution has given it to us. It's sort of specialized for processing speech sounds in ways that other sounds aren't processed. And this is really the foundation for reading, but reading has some extra components to it. One of the things just to remind you of is that as we develop, there's a real developmental specialization of the left hemisphere in most people. We won't get into left-handers and people who are atypical and all those kind of good things. But the speech system really becomes very focal and very localized as you develop over time. And usually by the time you're a young adult, that process is mostly over. So reading is actually sort of built on top of this developing language system. So there are two sort of moving targets that we're focused on. One is the underlying language system, and the other part's the decoding part of reading that requires you to translate visual information into the language that we all use. Let me just quickly give you an overview of some of the issues here. One of the things is that in natural speech, more than one phoneme is integrated into a single sound. So the word bag, you can't really tell where each sound is coming from. It's basically not segmented in any kind of way in the normal speech string. So the hard thing for kids to learn is that there are components of language that you have to basically separate out in sound when you're starting to connect them to letters. There are no clues to the segmented nature of speech. It seems seamless, and when kids are learning to read, it's like, how are these letters and words connected to this? Because there's no boundaries on it. So what happens early on is in beginning to reading, you start to discriminate letters. You first have to figure out all the letters of your alphabet or sound system. And then you have to figure out where the phonemes are. and how do those phonemes, those units of sound and speech, map on to those visual information. And that's really sort of, y'all have all heard of phonics, and that's sort of the basics of early reading, and we call it sort of the decoding part of that. So the earliest education is focused on helping children understand that words have units of sound in them, and rhyming is the earliest of that, so kids learn to start rhyming early on. And then they have to start learning to discriminate letters and match the letters to those sound units. And that's sort of what early reading is about along the way. The interesting thing is that as you get more proficient, it becomes more automatic, because basically it's the letter patterns and orthography that's more important, because as y'all know better than me, the brain is sort of a pattern recognizer. And after you do a lot of reading, you start to understand that those words have certain patterns of letters that go together, and you start reading them and understanding them as units, not separating out each of the letters, each of the phonemes basically along the way. So the organization of the reading system is really shaped by the statistical regularities of the writing system that you're under. And all different languages have different statistical regularities in them, okay? So like in English, you don't usually have 3 consonants in a row. In other languages, that's not the case. And so our brains actually learn those patterns so well that you become an automatic word processor. And I'm going to show you an example of how that happens. English is sort of unique. It has 44 phonemes that produce all words in English, which is pretty good. So you have to learn those 44. Unfortunately, in English, there are 250 ways to spell those. So the word 8 is a great example. ATE or EIGHT? How confusing is that to a kid who's trying to learn how to match letters to the phonemes? So English is what they call a deep orthography. There's not a one-to-one relationship for most letters to most words. Spanish is the opposite of that. It's a shallow orthography, and it's one-to-one. Russian is another one.
Yeah, are we allowed questions?
Yeah.
You're allowed.
Yeah, so what do you think about transfer learning? Teach them first to read proper phonetic language, and then transfer them to the difficult hieroglyphical English language type and things like that. When the whole
You want me to get in trouble in the United States? Yeah. Yeah. So, yeah, so some people have argued, like we have, as you know, a lot of Spanish immigrants to the United States. And why don't we teach them first to read in Spanish, which is easier, and then let them learn English? Woo, that gets you in trouble around here. Okay, I won't even go there. We gonna.
Yeah, okay.
Yeah, we'll talk about that later.
Yeah.
Anyway.
For example, my nephew is his wife is Italian.
Yeah.
Right, but we speak English, right? And then she talks to kids in Italian, she talks to kids in Russian, and then they go to kindergarten and they picked up Swedish first, right?
Yes. The multilingual stuff is fascinating.
Exactly.
And we can talk about that because one is whether it's simultaneous learning like that, or is it sequential that you learn one language and then you learn a second language. And the brain development of those two different language systems are completely different, even though it may be the same 2 languages. So we can talk about all that too. Yeah, that's fun stuff. Anyway, so this is sort of the quick and dirty overview of what happens with learning to read. Now, if your English is good, you should be able to read both of those things.
The left one is harder for me.
Well, it may be because second language.
Yeah, I can read it very fine.
Okay. So both of these basically show that you don't need vowels basically, because they're just placeholders once you learn the regularities of the English language. So you're actually doing pattern recognition and sort of filling in the blanks on both of these. Okay. One is just a little different than the other. One is only taking away the vowels, and this is sort of mixing up and using the first and last letters as your cues for the regularities in English. So if you're a good reader, once you learn to read, you don't need really the phonics, okay? Unless you come to a Russian name or something that I can't ever figure out, and I need to sound it out or something like that. So a new word along that line. So what we're always trying to get at is to get kids and adults up to fluent reading in a language because it's automatic and you don't really have to do any kind of phonological processing or anything like that. Kids with dyslexia and those things don't do this. This is not easy for them to do. So if you really look at the literature, there's a humongous literature on reading in the brain. You'll find that there's some key areas that everybody focuses on. And you can see that they're overlapping with the language system. So the letter speech sound integration really is overlapping with the Heschel's gyrus and Wernicke's area. You have the word analysis area that's sort of the angular gyrus and those areas up there. You have the visual word form recognition, which we're going to talk more about, which really is the part that develops this automaticity and the statistical regularity learning. And then, of course, you have the articulation of phonological, so you can actually say the words. So these are the key sort of components that have to integrate when you're learning to read. Yeah.
So do the components stay the same for Braille or for like
Yes.
sign languages?
Yes.
Something else?
Yes.
There's only visual changes. But
Yes, that's right. That's right. Yep. So if you really get more technical, there are two routes for reading. One is the dorsal route, which is really sort of the phonological phonics route that you start with, and you learn how to read through that sort of phonological to visual translation, letter by letter, sound by sound kind of thing. And that goes through this, excuse me, let me go back, hopefully. Well, oh no, there we go, I got it. Go through the dorsal route is more the articulation, the phonology, the decoding, the phonics kind of approach. But once it becomes automatic, you're taking the ventral route. And most people really read faster if you're using the ventral route. So there's a developmental progression from using the dorsal to the ventral. And so this whole system, this dynamic changes over time. And you can actually see that happening when you're studying reading in kids along the way. And of course, we always have the white matter tracks there. And one of the key questions in a lot of the literature is whether some of the integrity of the white matter tracks in this system are not really strong and good in kids who are struggling to learn to read and adults who don't read basically very well. So one of the things we really look at are some of the DTI and white matter components of this system and trying to figure out, are there weaknesses or problems there? And I'm going to show you some examples of that. So how do we study this? Let me just give you a quick and dirty example. So one of the things is a very simple task where you show a picture of a dress, and this is a functional MRI task. You basically ask the question, same or different, drops, clearly dress, S, so the initial phoneme and the sign are the same, but you got to actually read the phonemes and know that that's not dress. Dream, of course, is different. You can also do auditory, and we have an auditory component where you basically say the word and ask the question, are they the same or different? And then, of course, you have that. And what you get is you usually get a very nice reading activation map of a typical adult reader based on this, and you subtract out the visual and you subtract out the different components, and you can look at different aspects of this. If you look at the printed words, you can get different sort of components of your evoked response or spoken words or picture cues. So we sort of know how to parse out different components of this processing of this information and these tasks. We also have done this, a lot of people have done this, in different languages, and you can see the overlap between the print and the speech is pretty high across all languages. And the reason for that is it really is mapping onto the language system. So reading is just sort of, taking over part of the language system along the way, regardless of the script that's being used, the language that's being processed or anything like that. There's some subtle differences there, but not that many. We also have tasks that even get down into the linguistics a lot more. And one of the things we're trying to do here is look at that dorsal tract versus the ventral tract and which one is in better shape for people who are struggling to learn to read. And you can see we do things like have stimuli. So basically you're looking at stimuli, sets of 4, and only if you basically get 2 in a row do you respond, because we're looking at attention also, trying to make sure they're focused. So you can have words that are orthographically similar, but they're phonetically linked. So all these rhyme. So that clearly sometimes get processed through the dorsal tract. And then you have this sort of orthographically similar but non-rhyming task, which basically goes through the ventral tract. And we can separate out all the different components of language, whether it's false fonts or we have some vocoded speech and all kind of other components of this, trying to separate out which parts of the reading process and the linguistic process are being affected in especially in people who basically are struggling to learn to read. So these are just examples of, we have a bunch of data with this kind of task in it if anybody's interested. And the good thing about having different tasks is you actually get different maps basically because you're looking at sort of different processes, but they do overlap in the different reading tasks depending on how you process and put those together. Now, one of the projects that we have proposed in the CREST grant is to get the Healthy Brain Network data set, which has a lot of reading measures on it, and really look at the development of reading over time with the kids between the ages of 5 and 12. Most kids start the early process of reading around 4 or 5, and usually by 10, 4th grade is sort of considered to be, it should be automatic by then. Clearly, some kids go a little longer than that. So we're going to look at some of the foundational components of the visual, spatial, and auditory language system connectivity here in the developing brain. And these are cross-sectional data. And we're really interested in the individual differences that can maybe specify markers of poor reading proficiency early on. Yeah.
Just curious question. You said by 10, but is the process gradual or there is kind of a phase transition? Because subjectively there is a phase transition.
Yeah.
By watching
in a lot of kids, there's a phase transition. You know, it's like all of a sudden they're reading. Yeah.
Well, like becoming fluent as you.
Yeah, yeah. Well, no, it's actually pretty linear. You know, it's curvilinear is really if you really want to get to it. Kids are really developing. I tell you what changes is their speed of processing and how automatic it gets, and then they peak out, and most of us peak out around 10 or 12, and we don't really get much faster about that. Yeah, yeah. So anyway, so one of the data sets we're going to look at is these that have kids at different ages and looking at all this issues around connectivity and how it predicts reading outcomes. Now, just to let you know, if you have a typical brain and you've done one of these sort of reading tasks and you look at kids with dyslexia, what do you see here? Got nothing going on here. And so one of the questions is, why do these children develop the activity and the activation of those components that are necessary in the linkages to develop reading? And it's an interesting question because there are two sort of main theories. Well, there are lots of theories. One of them is that there's something in this network that's hypo-aroused or under-aroused, and they're not making the learning and the connectivity that needs to be going on. The other side, of course, like most of these theories, is there's too much noise in the system, and they're not learning because there's too much noise and they can't separate signal from whatever. And so it's an interesting issue because you can actually do scans on young kids who are not learning to read, and you see this. And we've done a lot of studies where we've actually done our baseline scans, and we just finished one of these studies. Then we do very intense reading remediation and sort of state-of-the-art reading kind of interventions for lots of hours, and then we do post scans. And so we have pre-post scans with reading, heavy reading, like the state-of-the-art reading in the middle, and that's sort of the intervention studies we've been doing. And what's fascinating is some of the kids, they look like this pre-intervention, and then after intervention, you actually see that the network is starting to form. So the intensity has helped these kids start to learn to read, and you can actually see that signal in the brain, basically in the network that you're looking at. There are kids who don't, and we don't have a clue on how to predict which kids are starting to respond and which kids aren't. So you could spend a whole year doing these heavy duty interventions and this kid's not going to respond. And the question is, do you need to do a different kind of intervention, a different kind of program, or do something different for these kids? And we don't have answers to that. And so we're using a lot of this data to ask questions of prediction of which kids respond and don't respond to interventions like this. And so we have a whole 120 third and fourth graders, anybody interested, who've had this model, and we have this data on. So there's lots of interesting data here. Yeah.
Is this, like when you do see this sort of food, for example, is it only in reading? Because like there's two things going on, right? One is like with dyslexia, there's just symbol confusion or swapping of notation, and that's happening even when they're doing math, right? That's just about the symbols on the
Symbols,
page.
yep.
And in this case, you're remediating the
Reading.
reading component, and the reading networks are somehow tied up with language, which is not the same as math. There's no spoken version that you learn first, right? How does that map over? Like, if you fix it in the reading context, does that have anything to do with the symbol swapping
In math.
in the math context?
That's a whole different lecture, but I actually have data on that because we actually did an intervention as our control was a math intervention in a previous study, and we can talk about that because they actually co-vary in some ways. The symbolic processing is part of the problem, but it's also how do you attach meanings to symbols? In math, you're still attaching meaning to symbols, just like you do. It's not, yeah, well, it is spoken language. It's actually language. It's still based on language system about math and numbers. So, okay, yeah.
I have just a follow-up or a related question. Do we have a correlation of some trade-offs? Those who have dyslexia kids, they do something else better. Whatever else, I don't know. Is there anything?
There are some studies that suggest these kids may have better non-language kind of systems, basically, and math may be one of them. In fact, people have studied engineering schools and really shown that a lot of the kids in engineering school really have poor reading and compared to their non-reading abilities and those kind of things.
But they're not dyslexic, right?
Well, it depends on how you define dyslexic. We can get in. That's a completely different ballgame. Yeah. Because a lot of people say if you have average reading, you're not dyslexic. And other people say, well, if you're supposed to be, you gotta, you're 99th percentile in all these other areas and you're average in reading, is that dyslexia? And so it depends on their type of reading problems that they're running into. We can talk about definitions a lot, okay?
Can I ask one question? So
Yeah.
is dyslexia simply like basically whatever the symbol system, whatever the language, it is actually seeing symbols in the language?
No.
Oh, okay.
No. Dyslexia by current definition is a problem at the word level connecting the phoneme to the grapheme. The older theory was about sequencing.
Yeah.
It's not about sequencing. Yeah. It's about the phoneme grapheme connection.
Totally.
Yeah. So anyway, we have a lot of data, brain data, pre-post interventions, and one of the classic questions we're asking is, how can we predict which kids respond and don't respond to this intervention? And can we do that using some of this connectivity data and things along the way? And you can see that we have some kids who start to respond and then kids who just never respond. They just, no matter what we do. And these kids, it's not that they're not reading, they're reading, but they're reading very slow. They're reading, letter by letter, and they never really get the automaticity. So the question is, what are they doing? And so they're using alternative or compensatory systems. And that's another thing we're really interested in figuring out. What are they doing to do what they do? And just to give you an idea how messy this is, these are averages of different kinds of interventions over time. And this is a reading measure. But the blue, sorry, keep doing that. The blue lines are just all the individual differences among kids who are in these programs. It's just to illustrate there's a humongous variability here. And one of the things we're trying to do is understand that variability from a biological and educational and the interaction between the two. Okay, and how do you parse that all out? So this is, yeah.
I mean, what about gender?
Clearly, more boys than girls have this trouble, and we don't understand why. There's theories about that, but more boys with reading problems along the way. Yeah. We also want to use, because of this issue of change over time, we want to use the DevMind project database from ages 5 to 9. They have longitudinal data on the same kids in reading. And so they have a sort of normative database that we can use to look at sort of what we expect versus the kids who don't get it. And so we have great data here to really look at changes in individual developing reading networks using the longitudinal data from this data set. And, for our point of view, for those of us who are clinical, we're really interested in the early key predictors of reading proficiency, which are going to be the kids, because the earlier you intervene, the better. So if you have to wait to second or third grade before the teacher's saying this kid's not learning, that's a problem. If you can get them in kindergarten and really start heavy duty intervention, intensity is a big factor here in interventions that you want to do. So the earlier you could identify these kids, the better. And there's all kind of interest in that. Clearly, we talked about white matter track. You know, I told you that the integrity of these tracks is a question in certain nodes in this. And Nikki Arrington, who y'all all know over at CABI, she's sort of the expert on this. And so we do a lot of DTIs looking at tractography and FAA scores and all kind of other stuff, trying to get at this. Clearly, all the data out there says these kids who struggle to learn to read, their integrity of their white matter is different than typical kids who learn to read easily. But where those problems are and how that affects connectivity and the networking is an open question at this point in time. The other thing we're really interested in is variability. So this is our variability and our bold response on that task I was showing you with the dress. And Jeff Malins has done some of this work, because the question is, can we predict who's going to respond on these interventions? And if you take the mean bold response at the pre-intervention data versus the variability in that bold response, variability actually predicts better than the mean. And so there's a question about, does that represent some kind of flexibility in the system still versus some kind of restriction in the system? And we have a lot of interesting questions about how to get at that variability and how do we understand that variability. And the question, of course, where's the noise in this? If you really believe part of this is a noise problem, is it systematic variability, and how do we understand that? So those of you who are into this dynamic analysis, I'm waiting to have answers to all this question, okay? We also have been doing connectivity work. Lisa Krishnamurthy, who some of y'all know, has done some work on some adults. So we do have a set of adult data who are 30, 40, 50 years old who really never learned to read above about a 7th or 8th grade level. Okay, they've struggled their whole life. They've been in adult literacy programs, all this kind of good stuff. And if you look at their neighbors who come from their same neighborhood, have the same background, and you look at connectivity during reading, you can see that they have all kind of nice node connections with all kind of other components versus the struggling readers who don't have much connectivity work. And so there's a lot of interesting questions about, some people sort of suggest that these adults are sort of like, if you titrate out all the ones with mild dyslexia or mild biological based problems in learning to read, these are sort of like the genetic hardcore, you know, there's something really different going on with these people at the biological level. And what is that? They may be the group to really study in some ways.
Do you have, among the data that you're advertising, do you have data sets paired with eye tracking, and what were they looking at when there were end scans, and what was actually?
Not eye tracking, we just have the data. Well, we can tell you exactly what the task was and what they were looking at the time, but eye tracking we don't have in the scanner yet. Yeah, Vince is getting that for us, right, Vince? The other thing that Lisa Krishnamurthy has done, which I think actually is some of the most interesting stuff going on, and I'm hoping we can get more of this. She's my sort of MRS spectroscopy person. And she's actually looked at these adults again, looking at connectivity, reading level, and GABA and glutamate, because we're interested in the relationship between sort of the connectivity and the neurochemistry at some of the nodes basically there. And there's some interesting relationships where in the struggling readers, the glutamate is too low or too high, depending on which node you're talking about. And the same thing with the GABA basically. And GABA, of course, as y'all know, has to do with inhibitory systems, and the glutamate has to do with more the learning kind of things. But there are differences in these systems in these folks who are struggling to learn to read compared to the typical learners. And the question is, how does that, you know, what I want to do is link the white matter, the neurochemistry, the connectivity across spatial arrays into this network and understand the entire network in some kind of ways. You ready to do that, Robin? Okay, okay. And last but not least, we are starting to do some, you know, if you got these systems that are either under aroused or over aroused or whatever it may be, can you activate them or can you inhibit them so that learning can take place during some of these interventions? So we actually have started looking at TMS as one of our options for treatment, as an adjunct to treatment. So we're still doing the reading intervention, but we want to do it while they're under TMS stimulation, basically, along the way. So and Nikki's been doing a lot of this work. So basically, we've been scanning subjects, we've been giving them TMS, and then of course we've been looking at what the effects of the TMS on the scan, and we actually have a study that we're going to be doing as part of CREST about this. But what we're gearing up for, and we've been looking at, is which part of the network do we stimulate or inhibit to improve reading outcomes? And we have a whole series of studies going on right now about that. And then the question is, if we can find the right combination there, what's it doing down to the rest of the network? And then how do we do interventions during that period of time of stimulation, basically, to maximize learning so that they actually can do that? So clearly, RTMS can prompt compensatory or enhanced processes. We know that. We don't understand how it all works. We're hoping that some of our data that we have with TMS and imaging, y'all can help us figure that out. We are going to use the TMS to do a protocol for CREST. And let me just tell you real quickly, there are two parts of it. Day one is going to be mostly baseline with EEG. We're going to include EEG at the same time so we can actually look at scans and EEG analysis together. And we're going to have the two different kinds of rest. Whoops. Sorry about that. Oh no. I went too far. Sorry.
Must have just jumped off the last slide.
Yeah. Let me see if I can get it back.
Like the sound effect.
Yep. There we go. We're going to use two different kind of resting states because there's a lot of question of whether the Inkscape and the standard fixation are really same or different, and does it affect things in different ways when you're looking at that. We have the reading task that we were talking about, and we're getting some other components of the scan, basically, just to get sort of the co-EEG MRI analysis while reading kind of thing, so we can look at that data. And then a second day, we're going to do sort of a pre-scan. And we have everything from ASL to GABA to DTI and resting state in here, along with reading. We're going to do TMS in the middle and then bring them back in the scanner and rerun the same sequence, basically, to look at pre-post changes with TMS to really understand better what's going on during that time. So those are sort of like the three main sort of areas the CREST study is going to give us.
Are we including confusion in here at all? Did we?
I thought we did.
You know, I just don't see it here listed. Maybe it just didn't on the.
DWI.
Oh, there at the bottom.
It's there. Yeah.
Got it. Okay.
Yeah, it's there. Yeah. I think we got everything but the kitchen sink in here.
Yeah.
Now, one of the things that Vince is working on with Nikki is basically, and the group at Tabby, is to try to get a scanner protocol that lets you do TMS in the scanner. So you can actually do in scanner protocols. And that's sort of state of the art right now, kind of stuff.
This little TMS happens here text is really code word for Nikki running around getting folks in the scanner.
Well, she takes them out, she scans them, she takes them out, she puts them back in. What we want is scan them during the TMS and keep scanning.
Scan, zap, scan.
That's right. That's what we really want.
When did you have DTI before as well?
The question is, do you really think it's going to change that much with TMS? One scan, there may be something there, but not many people think you're going to get one scan. Now, if you do multiple TMS series over time, like they do in depression and other things, you would expect changes. But one time, it's just how much time we can get people in the scanner, basically. We're sort of maxed out at 1.5 hours, so we're getting close to what we are there. And that's my story.
Cool.
Help me. Questions, comments, other questions? The audience is being very quiet.
Hey, Robin, this is Lisa here.
Hey.
Virtually. Hey, question. Very interesting talk. Thank you. For your last protocol, which region are you going to stimulate?
Robin closed the window. We're going to get back in.
Oh. which region are you going to stimulate? And then are you going to,
Can you hear me?
yeah,
Hold on a minute, because Robin
you closed
closed the
out.
window, so we've got to reconnect.
Okay.
Sorry about that.
Sorry about that. I think we're doing SMG, Lisa. I think that's what we decided, mainly because that's the data that we have that seems to be most interesting for looking at the sort of spread of the TMS effects across the network.
Okay. And are you going to?
Nikki may know. Is she on? I don't know if she's here. Yeah.
Yeah, Nikki here. That's correct. We're doing SMG.
Yeah.
Okay. And are you going to assess GABA in the SMG, or are you going to look downstream?
So we've talked about one or the other, but because we wanted to try to integrate this with the data that we already have that is over SMG,
Yeah.
that is kind of what we initially planned. But what we thought about doing is sort of doing some of each, and then, you know, talking to you about what you thought made the most sense, or what you thought would enrich the data that we have.
Yeah, no, I think this is super exciting. Do you know how long the TMS stimulation, the effects on GABA are supposed to hang around? Because I would recommend like trying to do a very short T1 in the post session, doing a very short T1 and then immediately getting GABA.
Yes,
to really look
that's
at
the
those
plan.
changes.
That's the plan.
That is, yeah, that's the plan. So we're doing theta burst stimulation, which lasts roughly, the effects last roughly about an hour. So, and based on some of the data we've already looked at, we're seeing that pretty good activation wise. We're seeing effects that last that long.
Nice.
But that's the plan in the post session, is to do the like, it's like a minute and a half T1 right before GABA.
Nice, awesome. And then fixation connectivity right away, because looking at those relationships in response to TMS is going to be fascinating.
Yeah, so the protocol is actually with the PID first, because we're sort of most interested in the reading network activation.
Yeah.
But ideally, we'll be able to get the reading task, the GABA, and then the resting state all within that hour period that we would expect the brain to still be under the effects of TMS.
Okay, then to be able to compare the pre and post resting state, since it'll in the post you're going to have an imprint of the task on the resting state, would you want to do that same order in the pre?
That is the plan.
Okay, awesome. Thank you.
Everybody wants their own order. That's what we found. We need to do about 10 of these series so that people can get the data.
Could you actually randomize the order across subjects, maybe?
Yeah, the problem is we have to run so many subjects. We get into lots of issues around order effects to start with, and then randomization, you have to get such large samples to do that, and we rarely get those kind of samples.
Fair enough.
Yeah.
And if there's an effect, I think you can still use it because it's systematically similar, and then you can put it as pilot data and get a grant, get a whole bunch more.
That's right.
Yeah.
We have a grant right now that everybody's involved in with UConn, and we're doing adults, college students mostly, who are typical readers, have a history of reading problems, but now seem to be okay, and then people are still struggling with reading. And they're coming in 5 times for TMS, basically, in different parts of the network, basically, to look at the effects on that. We're not doing interventions or anything, but we're looking at that. So we have humongous amounts of data right now because of the group at UConn and our data, basically, with TMS, if people are interested in some of that, with scans connected to it. So, yeah.
Well, yeah, and I think the other thing that will be really interesting is I don't think
Lee's on there.
So
Yeah.
we should look at data fusion as as well, like diffusion and fMRI, resting fMRI.
Yep.
Maybe using your CMICA approach, like,
Yep.
that'd be kind of interesting.
Yeah, there are very few studies out there where people are doing data fusion across different components of the data in this area. And the good thing is we know how to study reading. We can measure reading 1,000 different ways. And I mean, we're really very, very sophisticated in how we study reading. So measuring the behavior is easy compared to things like you do, Jess, schizophrenia, you know, those kind of things, much harder to measure and identify.
A little more subjective in the measurement.
Yeah. So the reading stuff is a lot more quantitative and easier to sort of correlate with and show relationships with.
Did you did you have time yet to take a look at any of the ABCD measures to see if there's anything relevant?
Yeah, there's some stuff there.
Yeah. Okay,
Yeah.
good.
Yeah. Yeah, that's another data set we can look at.
Right.
Yeah.
Hello,
Yes.
I have a question. Gracias. Nice presentation. So this study is focused on reading, meaning, people knowing how to pronounce words, and nothing to do with understanding of what they're reading, right? Is that my take?
We're not doing comprehension because we're mostly interested in the decoding part, which is the sort of underlying. To me, there are two parts of reading. One is sort of translating the visual into the language, and then there's the language comprehension part. Clearly, there's a whole group of people who have language impairments that have trouble with reading because their language has difficulties. And we do look at that. We measure those kind of things, but we're not really focused on the comprehension as a key factor, key component of these studies. We're really looking at the beginning stages of reading. Yeah.
And Robin, the words are really simple, right? Like, I mean, part of it is there's not so much confounding with comprehension. Just
That's right.
Everything is extremely simple.
That's right.
Whereas, you know,
Should we-
any
should-
English speakers know that.
Yeah, and you know, one of the classic things we do is nonsense words, which are phonetically accurate for English, but they're not real words because you have to be able to decode them to actually read them. So that's one of the classic experiences that you can't do those.
Exactly. It's I know.
Yeah. So yeah, we're interested in sort of the kickoff of reading. So like from the beginning stages to the point where automaticity starts to kick in. And that's really where comprehension, people who are slow readers and having to do phonetic reading, or people who are not very automatic and fast reading, their comprehension's affected because they just can't read quick enough to remember a lot of the stuff that they basically have read. So there's a lot of literature about the relationship between the automaticity in reading and comprehension in reading. And then there are people who have troubles with comprehension, and it's language comprehension. It has nothing to do with reading. But because reading sort of, you know, shares space with language, those people also have trouble with reading because they don't comprehend the language. So even if you did oral communication with them, they would have trouble understanding it. So there are lots of different factors here. Yeah, that's right.
We can think of any scientific paper.
Oh yeah.
Comprehension is super difficult to measure. My boy got 75, 17 out of 20 yesterday, and comprehension was wrong. I read this text and I don't know the answer. Yeah, he like read the text. What is the best idea? What like that describes what the author wanted to get. He's 9.
Yeah.
Like, well, they all fit. I don't know what the author was trying to get there.
Yeah.
And the teacher thinks it's the middle paragraph. I don't agree.
Yeah. One of the things I do in a class that I teach on reading and neuropsychology is I give a physics paper to the students to read, and they can read it. They don't have a clue of what it means. You know, so decoding is just sort of getting you into the language system. But if you don't understand the meaning of the words or the context or anything about it, you can't read it. You can read okay, you can decode all day, you can read out loud all day, but it doesn't mean you have any awareness of the meaning. So the two interact, and so you can have trouble in the language system, or you can have trouble in the translation system between the visual and the language. And I'm mostly interested in that first part, with the translation between the visual and the language.
I was going to say, given to make it more current, you could modify the task and have it be like a Wordle game.
Yeah.
This reminds me of salsa music singer from
Also,
Japan who didn't know anything about Spanish, but she sang in Spanish by memorizing the sounds.
Yep.
oh, interesting.
Yeah.
Yeah, people ask her, what do you think about the lyrics that you are singing? And she had no idea what she was singing at all. She just memorized the sounds. And
Yeah. One of my sons he does vocal coaching for opera singers, and he teaches them how to sing in all these different languages they don't know, because it's all
really?
it's all phonetic.
Hey, Robin, can you hear me?
Yeah.
This is Eddie Namias. Good to kind of see you. And my daughter participated in one of these back at CABI long ago, so hopefully she helped your data set.
Yeah.
I still have her picture of her brain on my wall. If I remember correctly, you're probably not using children who have dyslexia who are on any kind of medication that might be treating it. But I was curious if you've seen whether or not there are any medications that are helping, perhaps in combination with the TMS or anything else.
So that's a complex question, Eddie. Unfortunately, getting clean dyslexics is near impossible, because 40% of all the kids with dyslexia also have attentional problems, and a lot of them are on medication. So we don't discriminate with kids, and we just take them all. And one of the things we do is look at the data in relationship to whether they're on meds and what they're on and how much and all that kind of good stuff. If they can go off of it for the scans and stuff, we try to ask them to do that. But some of the kids, the big problem in the scanner, of course, is movement artifact. And if they don't have their medication, then we lose them as a subject because they can't do the task and can't stay still enough. So it's a trade-off. And there's lots of interesting data out there about the effects of medication in scanners with kids, and so we don't exclude them, mainly because of reality. Yeah.
I mean, you have a slide with a quite large range of data values, right? Maybe to tutorials.
Yeah. Yeah.
That could be one of them.
Yeah. Yeah, I mean, there's a lot of question of whether some of the white matter problems and issues we're talking about, or connectivity problems, are really causing both the attentional problems and the problems in learning to read. That it's all core. It's not really different diagnostic groups. It's really some underlying process that's affecting all these kids. And it just sort of, the symptoms are different in different kids in different ways. So we're not as big into the diagnostic debates as some people are, because we're not sure that current diagnostics really is helpful in any kind of way. Yeah.
Great, thanks.
Okay.
Any other questions? Suggestions, input? Great, well, thank you, Robin.
Sure.
This is great. So we are done for today, and then next week we are going to have a talk about data fusion led by Jean Liu and Jayu Chen, I think. So we'll see you all next week. Have a great weekend, everybody.
And food, right?
Hello, Vince. Have a nice weekend.
Yeah, we just have to decide when we want to start doing that. So
The crowd is growing.
huh?
The crowd is growing.
Well, row 4.
I know.
Right?
Well, last week there was only 3
Not
people
for
here.
next time, I'll be gone.
Yeah.
I'll be gone for 2 weeks.
Let everybody jump off. No, I don't know if Vanetta's going to be able to join today.
She was on there earlier.
Oh, she was?
I saw her.
Okay.
Yeah, she was on earlier.
Okay. I know she's buried in, I think, interview stuff as well. So, I don't see Kyle. Victor's here. James here. 11:30. Okay. Good. All right. Thanks for coming over.
Yeah.
Yeah. Let's just support the initiative, finally, right?
Yeah.
Awesome.
In person, it's much easier to ask questions.
Yeah.
You can get
All
much
right, so,
more.
I'm going to,
I have ongoing meetings non-stop.
What else is new?
Lab meetings.
Yeah.
take
Take care,
a,
Andrew.
Vince, I was wondering if I'm supposed to be helping out with one of the